This scientific paper addresses the problem of tracking mobile targets using unmanned aerial vehicles, UAVs, specifically focusing on the optimal use of a minimal number of UAVs. The paper is structured into several detailed sections, each addressing different aspects of the problem. Let's break down each section and provide summaries to ensure clarity. Introduction. Explanation. The introduction explains the necessity of tracking mobile targets using UAVs, emphasizing the importance in both military and civilian contexts. It introduces the novel approach of the paper, which focuses on using the minimum number of UAVs required for continuous tracking, even when the paths of the targets are known in advance. Summary. This section sets the stage by highlighting the significance of efficiently using UAVs for tracking purposes, presenting the paper's unique angle on tackling known target trajectories with minimal resources. Related work. Explanation. Here, the paper reviews previous research related to target tracking problems, TTPs, discussing various approaches and limitations found in existing studies. It points out gaps in the research, especially the lack of focus on optimizing the number of mobile trackers. Summary. The section provides context by reviewing existing literature, indicating how this paper intends to fill specific research gaps by focusing on the optimization of UAV usage for tracking tasks. 3. Problem formulation. Explanation. The core problem is formally defined here. The authors differentiate two types of target tracking needs. Class 1, where targets need continuous tracking during observation, and Class 2, where targets must be tracked at least once. This section sets up mathematical expressions defining how targets and UAVs are represented in a theoretical space and time framework. Summary. This section crucially defines the different tracking problems being tackled, laying the groundwork for the development of specific algorithms to address these challenges. Solution technique. Explanation. The authors propose a solution that involves formulating the tracking problem as a network flow problem. They describe in detail how to construct a graph representation of the tracking scenario, where nodes represent potential UAV positions and edges define possible movements based on UAV capabilities. The solution involves finding the minimum flow in this graph, which corresponds to the minimum number of UAVs required. Summary. The paper proposes a detailed algorithmic approach by converting the tracking problem into a graph problem, which allows the use of well-established mathematical techniques to find optimal solutions. Hatched experimental results. Explanation. This section describes the simulation studies conducted to evaluate the performance of the proposed algorithms. Different scenarios are tested to ensure robustness and efficiency, and results are analyzed to confirm the effectiveness of the proposed solution in reducing the number of UAVs needed for effective tracking. Summary. Real-world applicability of the theoretical solutions is tested here, providing evidence of the efficacy and practical value of the proposed methods. VA. Conclusion. Explanation. The conclusion summarizes the findings, reiterating the novelty and importance of optimizing UAV usage for target tracking. It also suggests potential future research directions to further refine and expand upon the current work. Summary. The paper wraps up by emphasizing the contributions made to the field of UAV-based target tracking and suggesting pathways for further investigation. Overall summary of the paper. The paper addresses the challenge of efficiently using UAVs to track mobile targets by minimizing the number of UAVs required. Through a detailed formulation of the problem, leveraging network flow theory and extensive simulations, the research demonstrates effective strategies to achieve significant resource optimization in UAV deployments for tracking tasks. This has broad implications for both military and civilian applications where such tracking is crucial.